Check it out now, y'all.
nanoHUB-U, online instruction.
Today we're here to talk about the approach curve, the physics behind what happens when a substrate is brought close to a cantilever, and when the cantilever has a tip on it and the tip interacts with the substrate. We'd like to try to systematically unravel all the effects that are going to happen, and when you just do this very simple experiment. And we're going to try to illustrate some of the important quantities that you might be able to derive by analyzing this so-called force versus displacement curve. So to begin with, I'd like to re-emphasize the coordinate system that we're going to use and the notation that we're going to use. And that's done in this particular slide. In particular, the deflection of the cantilever is going to be called small q, and q is going to be a sign quantity, which means it can be either positive or negative, because the cantilever can bend down if it experiences an attractive force between the tip and the substrate, or it can bend up if it experiences a repulsive force. All right, so q is going to be a sign quantity. The quantity that's of real direct interest to understanding the tip sample force between the tip and the substrate, that quantity is referred to as small d in this lecture, and this is the quantity that you have to infer, you have to figure out from your experimental data if you want to interpret your data in terms of this tip sample interaction force that's a very fundamental quantity. So I think to begin with, what I'd like to do is I'd like to first of all clarify the coordinate system and the convention that we're going to try to follow regarding the polarity of Q. So we're going to say that if the tip is far from the substrate, there's no deflection of the cantilever, and the separation between the equilibrium position of the cantilever and the substrate is indicated by this parameter z. If you turn on the tip sample force interaction, let's say that interaction force is attractive, then the cantilever is going to bend toward the substrate by an amount q, and the polarity, or that quantity q, if it bends towards the substrate from the equilibrium position of the cantilever, that's going to be considered a negative value, so that's negative q. And so therefore, in order to infer what the tip sample separation is, you have to subtract q from z in order to get d, right? So this diagram is really important to understand. It basically sets the algebra for the entire discussion that we're going to conduct here. So what happens when you position the cantilever a certain distance z away from a substrate? Well, there's an interaction force, and let's pretend we don't know the exact shape of it, but it's going to have a shape something like that indicated by the dark line in this slide, right? We position the cantilever a distance z away from the substrate. We then imagine turning on the tip sample interaction forces. According to the black line, those tip sample interaction forces for the particular value of z that we have set, those tip sample interaction forces are attractive. That's going to pull the cantilever toward the substrate. It's going to pull the cantilever by an amount q, as I've indicated. And q, the amount q that's going to result is going to depend on the magnitude of the tip sample interaction force and the spring constant k of the cantilever that the tip is attached to. Right? So basically what's going to happen, I try to indicate it schematically in this free body diagram in the top right-hand part of this slide. Right? The tip sample interaction force has to be exactly balanced by the restoring force of the cantilever, and that's going to determine how much the cantilever bends, right? So In this discussion, you have to somehow keep straight in your mind the distinction between Z and D. Very often in published literature, the distinction is not made clear. It can be very confusing, but if you follow a uniform sign convention, uniform notation, hopefully the distinction between Z and D will be clear. And in particular, if you want to determine what D is for a given Z, what you have to do is you have to draw a straight line centered at Z, at some particular value of Z. That straight line is indicated by that red line on this chart. The slope of that red line is, of course, going to be the spring constant K of your cantilever. And where that red line intersects the F versus D curve, right, that's going to determine the displacement of the cantilever Q. And it's also going to set the distance D that the tip is from the substrate under equilibrium conditions. So in this discussion, it's difficult, right, because you've got Z, which is what you set experimentally. D is what is determined from the force versus distance curve and the spring constant K of the cantilever. You want to be able to distinguish between these two things, and so what I tend to do is I tend to plot Z and D on the same axis, with the understanding that if you're measuring D, you have to use the result that's indicated where the red line intersects the force versus distance curve. Z is what you set. You can determine that experimentally because you can adjust the position of the substrate with respect to the cantilever, and that's under your control. So you control Z, the system is in equilibrium at the tip sample separation D, and the whole trick in this business is to infer D from Z. Now, it should be clear that the Z equals 0 position is completely arbitrary in this discussion. That's determined by your instrument. It's determined by the coarse approach of your instrument as the tip approaches the sample, right? What you call Z equals 0 is arbitrary, and basically it's unknown. So you don't have a clue where Z equals 0 is on this graph. And because D is related to Z by this equation that I've marked down here in red, right? If you don't know the Z equals 0 spot or position, you also do not know the D equals 0 position. You do know where Q is equal to 0. That quantity is known. So one of the problems in discussing this in a systematic way is that there are different conventions for setting D equal to 0 in these force plots, and we'll try to make our convention clear as we work through the discussion. So this is an important slide. It basically sets it sets up the rest of the lecture. If you understand what's going on here, then you shouldn't have too much difficulty following what I'm going to say in the next 15 minutes or so. There's an interesting phenomenon that occurs when the tip approaches the sample, and that phenomenon is referred to as jump to contact, and I'd like to describe how that comes about. So what you have to imagine is, let's say that the black dot shown on this slide is where you set some arbitrary Z value, right? That arbitrary Z value, when you turn on the tip sample interaction force, will cause the cantilever to bend through a distance Q, as I've indicated, right? So the cantilever actually bends closer to the substrate. And it's possible that after the cantilever is deflected, the cantilever position will be located by this gold dot labeled A on this slide. Now this gold dot labeled A is a special spot on the F versus D curve, because at that particular point, the slope of the cantilever exactly matches the slope of the F versus D curve. And whenever that happens, the situation is unstable, and any slight perturbation in the system will cause the cantilever to jump, literally jump from the position A to the position A prime. And this is referred to as jump to contact. And of course, it's solely determined, where that occurs is solely determined by the cantilever spring constant K and the detailed shape of that tip surface interaction force. Once the tip has jumped into contact with the substrate, the tip is now located at the D position given by A prime. You can continue to adjust the sample with respect to the cantilever. You can move the sample closer to the cantilever. You can load the cantilever so the displacement of the force that you actually apply to the sample increases, because now you're loading the cantilever against the sample, right? You move up to some spot that's indicated schematically by this red dot. At that point, you stop approaching the substrate to the tip, and you start to retract it. And as you start to retract it, you'll basically follow this force versus distance curve. And again, there's going to be a point on the force versus distance curve where the slope of the cantilever exactly matches the slope of the F versus D curve. That's indicated by the blue line in this particular diagram. And at that point, the tip will then jump out of contact with the substrate, right? There will be a jump from the bottom of the force versus distance curve all the way up to some other value. And that's how the tip snaps loose. So I try to make that a little bit more clear in this diagram. The upper part of the curve shows you the approach and retrace portion of the experiment. You systematically decrease the distance between the tip and the substrate by systematically decreasing z. For every value of z, the cantilever responds, and that gets you a particular value of d on this force versus distance curve. You've got two abrupt changes in d. One occurs in the jump to contact indicated by the gold-colored arrow, and then one is a jump away from contact, the pull-off, right, in the retrace curve indicated by the blue arrow. The bottom curve is what you measure experimentally, right? So the bottom curve is basically just the cantilever force, which is the displacement of the cantilever, as a function of this tip sample displacement z. So we've made no effort now to try to translate z into d, even in a schematic way, right? And so experimentally what you'll find is that as you move, if you start off with some large value of z and you systematically change z to bring the substrate closer to the tip, you'll see that the cantilever force or the cantilever deflection will start to be a negative number, indicating that the cantilever is pulled toward the substrate. At some point, you're going to experience this very abrupt jump to contact, indicated by that dotted, indicated by those gold circles. After the tip has jumped into contact with the substrate, you continue to load the tip against the substrate. You follow the straight line curve, and then on retrace, as you come back, you have to unload the tip from the substrate. Tip will stick to the substrate because there's an adhesive force. So, or in principle, there could be an adhesive force, right? So the retrace curve will not jump away, the cantilever and the tip will not jump away from the substrate at the same point that the tip jumped into contact with the substrate in the approach. So it's inherently a hysteretic process, right? And you end up experimentally measuring a curve that's indicated in the bottom panel of this slide. The pull-off force feature is very interesting, right? Especially if you remember the discussion in week 2 of this course, because the magnitude of that pull-off force gives you basically the adhesive force that's holding the tip to the substrate. So the problem is, what comprises that adhesive force, right? So I try to indicate that in a very general way here, because that adhesive force could have different components. There could be an electrostatic component if, let's say, the tip is charged with opposite polarity with respect to, let's say, a feature on the substrate. Of course, there's going to be the van der Waals interaction that we discussed in week 1. There could be capillary force acting between the tip and the substrate if you're doing these measurements in ambient conditions. So we talked about the capillary force at the start of week 3. There could be chemical forces depending on the nature, the chemical nature of the tip and the substrate. So all these forces can contribute to that adhesive force. And so just by measuring that adhesive force, it's hard to isolate which of these forces are dominant. What you can say, though, is that if the van der Waals forces dominate, right, and this is the best you can hope for. If those van der Waals forces dominate, then you can use a particular model to interpret the adhesive force in terms of some very fundamental quantities. So for instance, I just remind you about the DMT model and the predictions of DMT, right? The adhesive force due to DMT, which is solely van der Waals interactions, right, is just 2 pi times the radius of the tip times this quantity W132, which basically measures how much energy is required to pull a tip of radius r tip away from a substrate, right? So the naming conventions for W132 that we discussed in week 2 of the class, I just bring back here just to remind you what in principle you could measure if you can convince yourself that the van der Waals force is dominant in this adhesion of the tip to the substrate. So a lot of effort is expended into making this approximation valid, right? So you have to have good control of your tip, good control of your substrate, and if you do that, then you can start to measure something that's quite interesting. How do you avoid this jump to contact feature? Well, the simple answer to that is you have to use a stiffer cantilever, and I try to illustrate that in this particular diagram. So here I've got my force, my tip sample force curve indicated by black. Again, I show that you can control Z. You set that experimentally by your AFM instrument. You'll position the tip with respect to substrate at some arbitrary value of Z, right? And now in this case, we have a stiff cantilever, so the slope of that straight line that's going to govern the motion of the cantilever, right? That slope has got a much higher value to it than it did in the previous slide. Consequently, the displacement of the cantilever, right, which is indicated by the intersection of the red line with the black force versus distance curve, that deflection of the cantilever indicated by the parameter minus Q in this slide, that's going to be much smaller than it was in the previous case because the cantilever is stiffer, right? You don't have to bend it through as much Q, through as much distance in order to achieve the same restoring force. So the point is that with a stiffer cantilever, as you systematically approach the tip to the substrate, as I've indicated schematically by these different colored dots, right? With a stiffer cantilever, the curve that describes the deflection of the tip intersects the force versus distance curve only at one point, right? And because it intersects the force versus distance curve at only one point, you will not experience this jump to contact phenomenon, right? Basically, the slope of the cantilever never matches the slope of the force versus distance curve, so the jump to contact will not occur. Of course, the downside is you lose sensitivity when you do this because the deflection of the cantilever to acquire a certain balancing force is much smaller. So as a result, you're not as sensitive to displacement, or you're not as sensitive to small forces as you were if you use a softer cantilever. How stiff of a cantilever might be required? Well, you can do simple models to estimate that. I just run through a simple calculation that's easy to perform. So on the left-hand panel here, I just show typical van der Waals attractive interaction forces. I select 3 or 4 actually three. I picked three different values for the Hamacher constant. The interaction force between the tip and the substrate is given, of course, by the formula at the top of the page. This is something that we discussed in week 2 of the course. The slope of the interaction potential, or in this case, the slope of the interaction force, is very easy to calculate. You have to assume a radius of the tip. In this case, I just picked a 6 nanometer tip just to pick a number. And so what you can do is you can then run out a plot that's shown in the bottom right of this slide, which shows the spring constant K that you would need in order to prevent jump to contact for any tip sample separation for the different values of the Hamacher constant that I selected. And what you can conclude from this is that you typically need spring constants on the order of, as the tip gets closer to the substrate, right? As the tip gets closer to the substrate, the spring constants have to be 10 to 100 newtons per meter in order to prevent jump to contact, right? So if you want to achieve this condition, you're going to need spring constants that are on the order of 10 to 100 newtons per meter for typical values of van der Waals interactions that you might encounter. I'll just end the lecture by saying there's a possibility that we haven't described, and this is particularly important if your sample is very soft. We've always assumed that in calculating the tip sample separation, we've always assumed that D is given by the difference between Z and the deflection of the tip. But in principle, if the sample is soft, the sample could also distort. It could pull up in some way that I've schematically indicated here. And if that happens, right, then there's a deflection of the sample that also has to be taken into account. That's a much more complicated problem, but that would then cause you to alter your definition of what D is, as I've tried to indicate in this equation. So that's something that you have to be concerned about, especially if you're looking at thin, soft layers on substrates or very soft substrates themselves. So that's all I wanted to say about in trying to understand this very fundamental force versus displacement curve and how to convert the force versus displacement curve into a force versus gap, or force versus distance between the tip and the substrate. That's the fundamental thing, right? This is the initial attempt to describe that whole process. What we're going to talk about next is we're going to focus on this jump to contact feature and try to understand it a little bit better, and then we're going to come back and go after this force versus distance, force versus displacement curve in more detail and show you how to take your experimental data and extract out useful information. So we'll see you for the next lecture. Thank you very much.